Okay, so in this one, we're going to talk about conditional probability and independence. Going to do some tree diagrams, going to do some formulas, lots of details. All right, so let's head back to the pierced ear male-female problem. Got some probabilities listed at the top. Probability that you're male would be all the males out of all the kids. Probability that your pierced ears, it's all the pierced ears, 103 out of all the people. All right, now let's review these little union and intersection symbols. So the probability of A, now when it's upside down, that's intersection. So the probability of A intersection B, which is the probability of males and they have their ears pierced. So I'm going to go find the males that have their ears pierced, and that's 19 out of 178. Then I've got the union, which is the probability that you're male or you have your ears pierced. And so we're going to do all the males plus all the pierced ears minus the males and the pierced ears, because these two events are not mutually exclusive. So you have to subtract out the overlappage. All right, if we know that a randomly selected student has pierced ears, what's the probability that the student is male? Okay, so I already know that this kid has pierced ears. So I am now not out of 178. I am out of 103 because I know that the pool of people that I'm picking from has just gone to only people who have pierced ears. So here's how we're going to write this. So here's the stats part that you have to have. We are finding the probability that a student is male given, and that's the big word right there, given that they have pierced ears. Okay, so male, pierced ears, so that's going to be 19. Those are all my males that have pierced ears, but that's only out of 103. So what changed? Well, if I did the males and pierced ears, the top number is the same. So the top number is still males intersection pierced ears. The bottom number, however, isn't the total number of people. The bottom number is the pierced ears. So what I'm doing right now is I'm building the formula that I'm getting ready to hit you with. Okay, so males, given that I knew that they had pierced ears, so males and pierced ears, those are my 19. What changes is the pool of people you're picking from. It's no longer the general population. It's no longer the 178. Now it's only out of pierced ears because I know that everybody I'm picking from has pierced ears. Okay. What's the probability? Let's see. If we know that a randomly selected student is male, what's the probability that the student has pierced ears? Okay, so now we're flipping it around. So here's what I'm finding. I'm not finding the probability that you're male. I'm finding the probability that you have pierced ears given that I know you're male. Let's read this one more time. If we know that a randomly selected student is male, that's that part. What's the probability that that student has pierced ears? Okay, well, if I use this is going to be the probability that I have pierced ears intersection male out of, now this one was pierced ears because that was my given, so this one's going to be the probability that your male is going to be on the bottom. So pierced ears and males, that's still that good old 19 number, but now I need my bottom number to be all the males, and that's going to be a 90. All right, this is leading beautifully into the formula that I'm getting ready to give you. Conditional probability. The probability that one event happens given that another event is already known to have happened. So conditional probability means I want the probability of this given that I know that this has already happened. So the probability that you have pierced ears given that I already know that you're male. Or I want the probability that you're male given that I know that you have pierced ears. Suppose we know that event A has happened. Okay, if I know that event A has happened, then that is my given. Then the probability that event B happens, given that event A has happened, is denoted by P parentheses B and then a vertical bar long enough so that you know it's not an L or an I, A. And the way that you read that is the probability of B given A. So that bar means given. So the probability that a randomly selected student is male, given that the student has pierced ears, is the probability is male, given he has pierced ears. Okay, so now using the table from before, we can see that, now we have kind of already talked about this, is male, given, has pierced ears. So this is the number of students who are male and, that's a key word, have pierced ears, that's that 19 number, over the probability of your given, the number of students with pierced ears. We focus on the probabilities instead of the number of students, so the probability that you're male and pierced ears is 19 over 178. That's the 19 over the total number of kids. And then probability that you're pierced ears is 103 over 178. And then if you divide that, the 178s cancel and gives you the 19 over 103. I'm totally fine with you skipping this part and knowing that the ones that are male and pierced ears is the 19 and the probability that you're pierced ears is the 103. But just know that that's what's happening to get those numbers. Okay, so here are your formulas. The probability of A given B is the probability of A intersection or and B over the probability of B. Okay, the probability of B given A is the probability of B intersection A over the probability of A. So the top is the probability that they both happen together. The bottom is the probability of your given. Okay, we did this problem on the USA Today and the New York Times, and there's our Venn diagram. It says, what is the probability that a randomly selected resident who reads the USA Today also reads the New York Times? Now, when you read that, you've got to stop reading it like you're just reading a question. You have to read it like a statistician. What is the probability that a randomly selected student who reads the USA Today? So what I see, that's my given. What is the probability that a randomly selected student who reads the USA Today also reads the New York Times? Now, some people who read the USA Today read the New York Times, and some of them don't. The point is, I'm not talking about everybody. I'm only talking about the pool of people who read USA Today, and I want the probability of how many of them also read the New York Times. Okay, well, you know the formula. It's going to be the probability of New York Times and USA Today over the probability of USA Today. All right, let's look at my Venn diagram. Where is the intersection? Where is the probability where is the probability that the people read both of them? And that's this part right here. That's their intersection. That's what that means, intersection. So that's 0.05. Now I need the probability that we read the USA Today. Now, you have to be careful. It is not this number. This entire bubble represents the proportion of people who read the USA Today, and that total proportion is 0.4. And then when you divide that out, you get 0.125. So you have seen how you can do the given probabilities off of a two-way table, and now you've seen how you can do the given probabilities off of a Venn diagram. Okay, check your understanding. Students at the University of New Harmony received 10,000 course grades last semester. The two-way table below breaks down those grades by which school of the university taught the course. So in colleges, there are different schools. Like at Carolina, there was a school of education, there's a school of journalism, there's a school of business. So most of the time you go for 2 years and take your general education classes, and then you have to apply to the school that you want to get into. All schools aren't like that, but some are. So that's what this is talking about. Okay, college grades tend to be lower in engineering and the physical sciences, which they're going to call EPS, than the liberal arts and health and human services. Choose a University of New Harmony course at random. Consider 2 events. Now they're defining the events for me. E is the grade comes from an EPS course, and L, the grade is lower than a B. So they have defined 2 events. Okay, so I'm going to highlight those so I don't have to search for them. E is the grade comes from EPS. All right, and EPS is the engineering and physical science. So those are the tougher general classes. And then L is the grade is lower than a B. Okay, here are my questions. Find the probability of L. Interpret this probability in context. Find P of E given L and P of L given E. Which of these conditional probabilities tells you whether this college's EPS students tend to earn lower grades than students in liberal arts and social sciences? Explain. Okay, here's what I want you to do. I want you to push pause, and I want you to find number 1 and interpret its value. I think you can handle that. And number 2, I want you to find P of E given L, and I want you to find P of L given E, and I want you to think through the second part of that question, and then hit play. But try this on your own. Okay, so the probability of L is the grade is lower than a B. Okay, now we have to show our work here. So the probability of L grade is lower than a B. Those are these guys. So 2268 plus 800 plus 588 over, I think they said we had 10,000 people or 10,000 grades. Yep, received 10,000 course grades. So out of a total of 10,000. And that's 3656 over 10,000, which is 0.3656. To interpret that value, and you should already have your sentence, so you're just checking against what I'm getting ready to say, there is a 0.3656 or a 36.56% chance of selecting a course grade that is below a B. Okay. Now we're going to find probability of E given L and L given E. Okay, E given L is going to be the probability of E intersection L over the probability of L. So E's and L's. Okay, so I am, let me highlight this. I am engineering and physical science and below a B. There are 800 of me. over the probability of L, and L is that I am below a B. Or yeah, I am the total number that is below a B. 3656. And I divide that out, and I got 0.219. So, it didn't ask me to interpret this. Just reading to make sure. Nope, it didn't ask me to interpret this. But here's its interpretation. There's a 21.9% chance that I could choose what does E stand for? Engineering. That I can choose an engineering kid given that I know that their grade is below a B. Yep. All right, so now I want probability of L given E, which is the probability of L intersection E over the probability of E. Well, that's still 800. And E. E is that I'm an engineering kid. Engineering. So I have to add 368, 432, and 800. And I got 1600. And that gives me 0.5. Which means there's a 50% chance that, given I know that you're an engineering kid, you got a grade lower than a B. It says, which of these conditional probabilities tells you whether this college's EPS students tend to earn lower grades than students in liberal arts? And I would look at the second one, because that's the probability of getting a low grade given I know you're in this engineering program. Okay, so take a second, pause it, write that down. Make sure you're good with all this, rewind, do what you got to do. Okay, now let's talk about the general multiplication rule. So we've done givens, awesome, because we need givens to be able to do ands. The probability that events A and B both occur can be found using the probability of A and B, which is also written as the probability of A intersection B. Okay, here's your formula. It's the probability of A times the probability of B given A. I'm pretty sure that's on your formula sheet. What this rule means is that for both of two events to occur, first, one has to occur. Then, given that the first one has occurred, the second one has to occur. Okay, so here we go. Here's my first event. Okay, so that one's going to occur. Now, for A and B to both happen, it's the probability that the first one happens times now the probability that the second one happens, given that the first one has happened. So it's not just the probability of the first times the probability of the second, because the second one can happen without the first one happening. So I can get a B, but not be in the College of Engineering, or below a B. So it's the probability of A times the probability of B, given that A has happened. Okay, teens with online profiles. The Pew Internet and American Life Project find that 93% of teenagers, ages 12 to 17, use the internet, and that 55% of online teens have posted a profile on a social networking site. Okay, that was a given. Like what we just read, that was a given. 55% of online teens have posted a profile on a social networking site. That means that 55% is the probability that you have posted a profile given that you're online. Only 93% of us are online. Us, like I'm a teenager. So only 93% of the teenagers are online. Of those 93%, 55% have posted an online profile. The 55% is not out of 100% of teenagers. Find the probability that a randomly selected teen uses the internet and, there's the kicker, has posted a profile pic. Okay, so I haven't defined any events yet. And so instead of doing that, I'm just going to use words. So the question says, find the probability that a randomly selected teen uses the internet, so I'm going to put online, and has a profile. So I'm not defining events. I'm not using like A and B. I'm just going to use words. Okay, so formula first. This is going to be the probability that you're online times the probability that you have a profile given that you're online. Okay, and the other way you can write this instead of the word and is that intersection. I just want you to be fluent. I want you to be comfortable with both. I know you're already thinking, well, I wonder if we have to write both. No, you don't. You don't. But I need you to be able to read both. I know that they are both. I need you to know they are both options. The formula has to look just like that. No other option. Okay, so now let's see what information they give me. What is the probability that a teen is online? Use the internet. 93%, 0.93. Okay, now I need the probability that they have a profile given that they're online. Well, it says 55% of the online teens have posted a profile. So there's my 55%. And that gives me 0.5115. Now, I do not want you to sit here and think, oh, well, you just take the two numbers that they give you and you multiply them together. No, absolutely not. You have to think. Sometimes you have to do 1 minus the 55 and then use a 45%. Like you have to read, you have to think. This is not a, oh, well, when I see this, I just always multiply these two together. Please don't think that. Okay, serve it up. This is one of my favorite problems. This entire page is all based on this one problem. So this is a fantastic example of a full-on FRQ. It's going to have you set it up, and then it's going to ask you 3 questions about it. Okay, so this is a great FRQ. Tennis great Roger Federer made 63% of his first serves in the 2011 season. Made 63% of his first serves. When Federer made his first serve, all right there, I see the given. Given that he made his first serve, he won 78% of his points. When he missed his first serve, there's another given, and had to serve again, he won only 57% of his points. Suppose we randomly choose a point on which Federer served. Okay, randomly choose a point. So he is still winning points. Sometimes he's not. So I'm talking about after he has served or had to serve twice, I'm choosing the fact that he won a point. However it is that he got there. And he could have gotten there 2 different ways. He could have won the first point or won the first serve and then won the point, or he could have lost his first serve, had to serve again, and still won the point. So what I'm going to do here, I'm not going to make a 2-way table, and I'm not going to make a Venn diagram. When you see this 2 events kind of a thing, one after the other, you're going to use a tree diagram because it works beautifully. So here we go. We have his first serve. And feel free to just watch, and then when I'm done, pause it and write this down. Like that would be a great way to do this. Okay, so first serve. He either makes it or he doesn't. So makes first serve, misses first serve. Okay, after he makes his first serve, he either wins the point or doesn't. And after he misses his first serve and he has to serve again, now it doesn't give me information about his second serve, but if he misses his first serve and has to serve again, then he either wins the point or he doesn't. There's my tree. So you guys can see the first event is his first serve. The second event is wins the point or not. So now let's put some numbers in here. Tennis great Roger Federer made 63% of his first serves, which means he missed 37%. Okay. When he made his first serve, so that means this event has happened. So I'm here. He has made his first serve. He won 78% of his points, which means he did not win 22% of the points when he made his first serve. Okay. When he missed his first serve, so now we're down on the bottom branch, and had to serve again, he won only 57% of the points, which means he lost 43% of the points. Now, let's stop here for just a second. You want a cool job? Go major in statistics and go be a statistician for an NFL team or an MLB team. What's the movie? Is it Moneyball? Is that what it is with the baseball? And it's got Brad Pitt. Great movie. And it's all about statisticians and how to choose a player and how much money you should pay that player. It's a great, great, great movie. If I was a teacher that showed movies in class, we would so watch that movie, but I'm not. Maybe after the AP exam we'll watch it. Okay. So now here's the questions. What is the probability that Federer makes the first serve and wins the point? Okay, here's the kicker. You can't just give me an answer. You can't give me naked math. You have to translate that English into statistics and then show me where the values are coming from. So here we go. Now I have not defined events, so I'm just going to use words. Probability that he makes first serve, and there's that word, and, so I'm going to be fancy pants and use my intersection, and wins point. Okay, that is key right there. Like on an FRQ, that'll get you 1 point right there. You're taking the English and you're translating it into statistical lingo. Okay, so now I'm going to use my formula. So intersection means I'd find the probability that he makes first serve times the probability that he wins the point given that he makes the first serve. Now this is where if it hasn't kind of clicked, it should be clicking in the next 2 minutes. Okay, makes the first serve. Well, what's the probability that he's going to make his first serve? 63%. Okay, now, do you guys see the probability that he wins the point? Look at your tree. He can win the point 2 different ways. He can win the point here, or he can win the point here. I'm not interested in the bottom one. I want to know the probability that he wins the point given that he made his first serve. So I want the 78%. I don't want the 57%. And I'll have some people who'll add 78 and 57% together, which so doesn't make sense because that's over 100%. Like, that doesn't make sense. It's not 78% of the time he wins the point. It's 78% of the time that he makes his first serve that he wins the point. 57% of the time that he misses his first serve, he wins the point. So that's not 57% out of 100, that's 57% out of 37%. Okay, light bulbs should be going off if they haven't already. So the probability that he wins the point given that he made his first serve is the 0.78. And this gives me 0.4914. And I don't know why I went 4 decimal places, but I did. You have to be accurate to 3 decimal places. So I have a lot of students in the past who'll just go 4 to make sure that they're good to the 3rd decimal place. All right. When Federer is serving, what's the probability that he wins the point? Okay, now hold on a second. When he's serving, well, he's serving all of this tree. Every piece of data in this tree, he is serving, okay? What is the probability that he wins the point? Okay, guys, he can win the point 2 different ways, and that's what's highlighted. But please, I hope you already know that it's not the 78 plus the 57. He can win the point 2 different ways. He can win it if he makes the first serve and wins the point. Okay, now listen, this is an important word. I'm going to stress some words here, and let's see if you can see why I'm stressing them. Ready? He can win the point if he makes the first serve and wins the point, or if he misses the first serve and wins the point. Okay, I'm going to say that different. Watch this. He can win the point if he wins the point given that he made the first serve, or he can win the point given that he's missed the first serve. Okay, now here's where the wheels come off for a bunch of students. They don't know how to write this with statistical lingo, and that's what I'm going to be grading you on. Okay, so let's write what they're asking. Probability that he wins the point. Okay, so I want the probability that he wins the point given that he's serving. That can happen 2 ways. He could win point given makes first serve, or, okay, and hold on, I'm going to be fancy pants, or he can win point given that he misses first serve. All right, and now I'm going to use my tree. Wins the point, makes the first serve. That's this branch right here. So 0.63 times 0.78. There you go. That's the probability that he wins the point given that he's made the first serve. Okay, and then this is or, and or is plus. Probability of this or this is a plus. Wins the point given that he missed the first serve, so that's this one. So 0.37 times 0.57. And I want you to practice typing that in your calculator. I know that seems silly, but let's make sure that you can get this far and not screw it up. Again, I went 4 decimal places. Okay. Anything that you have a question about, I want you to star it so that you can ask me about it when we have class. What is the probability that Federer missed the first serve but still won the point? Okay, now think about this in terms of stats. Probability that he missed the first serve but he still wins the point. Okay, so we're going to find the probability that he missed his serve given that he wins the point. So that's going to be the probability that both things happen, missed and wins, over the probability that he wins. Well, and that's the neat thing about a lot of these FRQs is that they build on each other, because to find the bottom, the probability that he wins, remember he can win two different ways. Well, we found that in the question before. So this number right here and all this work, we don't have to repeat all this work. We can use that number because we have the work on this page to back up where that number comes from. And I have some students who are super paranoid who'll do this, especially if the parts are numbered. Let's see, A, B, C. They'll say from part C. If you want to do that, that's totally fine. Do not spin your wheels and show me where that number came from twice, because you're wasting your time. And the probability that he missed his first serve and still wins is going to be those two branches multiplied together. So 0.37 times 0.57 divided by the probability that he wins the point, and that gives you 0.3003. Okay, so let's take the idea of this tree diagram and let's apply it to another problem. And let's see if you can see the need for the tree diagram as we read this question. Because see how part A says draw a tree diagram? They're not going to tell you to do that. Okay, who visits YouTube? About 27% of adult internet users are 18 to 29 years old. Another 45% are 30 to 49, and the remaining 28% are over 50. A study found that 70% of the internet users from 18 to 29 have visited video sharing site, along with 51% of the 30 to 49-year-olds and 26% of the 50 or older. Do most internet users visit YouTube and similar sites? Question says, draw a tree diagram, find the probability that a person has visited a video sharing site. Given that a person has visited a video sharing site, find the probability that he or she is aged 18 to 29. Now, with the tennis problem, it was made his first serve and then won the point. Like, there were two very specific, and I call them events, very specific consecutive events. This isn't necessarily two obvious events, but there are groups, and then those groups are divided into groups. So that's how I know that this needs a tree. So I see 3 branches originally going into the 3 different age groups, and then I see 2 branches coming off of each age group for using the internet or not using the internet. So I'm going to tell you what I want you to do. I want you to pause this, and I want you to do the tree, and then I want you to hit play and check your tree against mine, and then I want you to pause it again, and I want you to take a stab at B and C on your own, remembering that the important part is being able to write like a statistician. Use the lingo, okay? So pause it and try your tree. All right, so I have adult internet users, and they are into 3 categories: 18 to 29-year-old, 30 to 49, and 50 plus. Then visits video sharing sites doesn't. Does, doesn't. Does, doesn't. 27%, 45%, 28%, 70, so that's a 30, 51, so that's a 49, 26, so that's a 74. Okay, now that your tree is the way that you want it, pause it and try B on your own. B says find the probability that a randomly selected person has visited. Okay, so has visited can happen 3 different ways. Probability visits video sharing sites. It's going to be the 0.27 times 0.70 If I were to put this in words, it would be the probability that you are let's see, 18 to 29 and visit. Probability that you are 30 to 49 and visit. Probability that you are 50 plus and visit. So obviously I would put the words ahead of the numbers. Sorry, got a little ahead of myself. And I got 0.4913. So the probability is about 49.13% of all internet users visit video sharing sites. Okay, all right, now pause it and try question C. Given that this person has visited a video sharing site, find the probability that he or she is 18 to 29. So I know you visit the site. And again, that's what we found in part B. See how that information builds? Find the probability that he or she is age 18 to 29. Okay, you kind of write it like a statistician. So here I go. I'm finding the probability that you are 18 to 29, given that I know that you visit visit video sharing sites. That is going to be probability that you are 18 to 29 and that you visit over the probability that you visit. That's a have to. Have to have that formula. Okay. 18 to 29 and visit is the same thing as the 2 branches. So 0.27 times 0.7, which is, and this is the same thing as if this were to come up, say, I don't know, on a multiple choice question, this and formula is the probability that you're 18 to 29 times the probability that you visit, given that you're 18 to 29. And that's what these 2 numbers are. This is the probability that you're 18 to 29, and this 0.7 is the probability that you visit, given that I know that you're 18 to 29. So that's that formula right there, and that's not an over, that's a times. I just ran out of room, so that is not a divide bar. Over probability that you visit, which was 0.4913 from part B. and I got 0.3847. Given that a person visits a video sharing site, there is a 38.47% chance that they are 18 to 29 years old. I'm going to read that one more time. Given that a person visits a video sharing site, there's a 39.47% chance that they are 18 to 29 years old. All right, we're still rocking. Here we go. Mammograms. Many women choose to have an annual mammogram to screen for breast cancer. After age 40, a mammogram isn't foolproof. Sometimes the test suggests that a woman has breast cancer when she really doesn't, which is a false positive. And other times the test says that a woman doesn't have breast cancer when she actually does, which is a false negative. Suppose we know the following information about breast cancer and mammograms in a particular region. 1% of the women age 40 or over in this region have breast cancer. For women who have breast cancer, the probability of a negative mammogram is 0.03. For women who don't have breast cancer, the probability of a positive mammogram is 0.06. A randomly selected woman aged 40 or over from this region tests positive for breast cancer in a mammogram. Find the probability that she actually has breast cancer. Okay, so here's what I see. I see all the women over 40, and then I see them going into two different groups. Before the mammogram, we know the probability that the women over 40 have or do not have breast cancer. So the first branch is going to be has breast cancer, doesn't have breast cancer. Now, if you do have breast cancer and you get a mammogram, you could get a positive test result or a negative test result. Okay, if you get a positive test result, then that is confirming that you have breast cancer. If you get a negative test result, then that is a false negative. Okay, then I have the women, the percent of women who do not have breast cancer, and they go get a mammogram. Now, if they test positive, that is a false positive. If they test negative, then that confirms they do not have breast cancer. So, pause this, go make me a tree. Okay, 1%, 0.01, so 0.99. Okay, for women who have breast cancer, the probability of a negative mammogram is 0.03. So this is a 0.97. For women who don't have breast cancer, the probability of a positive mammogram is 0.06. So 0.94. A randomly selected woman aged 40 or over from this region tests positive for breast cancer in a mammogram. So we know she's tested positive, so that's my given. Find the probability that she actually has breast cancer. So I'm finding the probability that she has breast cancer given that she tests positive. Read that one more time. A randomly selected woman has tested positive. Find the probability that she actually has breast cancer. So this is not an and, this is a given. I know that she has tested positive. What is the probability, knowing that she has tested positive, that she has breast cancer? Okay, think about your given formula. The given formula is the and on top, so probability of breast cancer and test positive over the probability of your given test positive. Now, this problem isn't as nice as the problems before. I mean, it's only asking one question. The problem is we haven't found the probability of testing positive, and that can happen two different ways. So I'm going to have to show all of that in this problem. Okay, so breast cancer and testing positive, if I look at my tree, which lines this up so nice, has breast cancer and tests positive. So that's 0.01 times 0.97. 0.01 times 0.97. And again, I just want to point out the and formula is the probability of breast cancer times the probability that you test positive given that you have breast cancer. And that's what this 0.97 is. The 0.97 is not that you test positive. That's going to be this guy down here. Those are two very different numbers. This given that you're tested positive means I'm tested positive given that I have breast cancer. So that's why it's the 0.97. Make sure that makes sense. These things that are circled right here are two very different test positives. This is the total probability that you're going to test positive. Okay, that could happen from having breast cancer and testing positive, or, stress that word as I write the plus sign, I could not have breast cancer and test positive. Ands and ors are so important. Okay, I recommend that you total the top, total the bottom, and then divide. Because when people do this in one swoop, they type it in incorrectly. 0.0097 over 0.0691, which is a 0.14, and I'm going to bet, because I only have two decimal places, the next one is a 0, because very rarely do I go two decimal places, because you're supposed to go 3. But y'all check me on that. Okay, I hope you're starting to get a feel for this, the givens and the ands. Those are the two big topics today, the givens and the ands. All right, last problem. A computer company makes desktop and laptop computers in factories in 3 states, California, Texas, and New York. The California factory produces 40% of the company's computers, and the Texas factory makes 25%, and the remaining 35% are in New York. Of the computers made in California, there's a given. 75% are laptops. Of those made in Texas, New York, 70 and 50% respectively are laptops. All computers are first shipped to the distribution center in Missouri before being shipped out to stores. Suppose we select a computer at random from the distribution center. Construct a tree diagram to represent the situation. Find the probability that the computer is a laptop. Given that it is a laptop, what's the probability that it's made in California? Okay, here's the deal. I want you to pause it, like for real, pause it. And I want you to do the whole shebang, the whole thing, and do not press play until you are stuck or you are finished. Go. All right. The thing that I did in blue is not required, but I just want to make sure that you understand that I'm still using the AND formula when I get that 40 times the 75. Because that 75, it's not the probability that it's in California times the probability that it's a laptop. That's not true, because I got laptops coming out of all three states. So I'm trying to make sure that you understand that this and this are two different numbers. Okay, this piece here very easily comes from the tree, and that's why I just do that. But know that I'm using the formula California times the probability that it's a laptop given that it's from California, and that's why it's a 0.75 instead of a 0.65. So that's extra. I just want to make sure that you understand that, because I could ask a very nice multiple choice question to make sure that you understand that crystal clear. Okay, whew, that was a lot. But I hope that you went at your own pace and digested everything. I know it sounds crazy, but it wouldn't hurt to just sit and watch this again, maybe fast forward and go through just the problems. I don't know. But this was packed full with some pretty big information, so make sure that it's all categorized and tucked away in your brain correctly. And we'll practice the problems in class.